ever get this feeling like reality is kind of weirder than we think it is?
Mm-hmm.
Like we assume a ball thrown in the air, it just follows one path, right?
Right.
But what if it didn't?
Yeah, okay.
What if, like, at the quantum level, it's taking every path at the same time?
Yeah.
That's the kind of head-scratching thing we're diving into today,
Yeah.
the superposition principle.
Right.
And to, like, guide us through this whole quantum weirdness thing, we've got excerpts from Feynman's 1948 paper,
Okay.
Space-Time Approach to Non-Relativistic Quantum Mechanics.
Wow, what a title.
Yeah, catchy.
Yeah.
Feynman, just in case anyone's not familiar, he was not your average physicist.
Yeah.
I mean, yeah, he won a Nobel Prize, okay.
Yeah.
But he also played the bongos
Mm.
and cracked safes.
Is that right?
Yeah, and just had this way of making even the most brain-bending physics kind of fun.
That's great.
So,
Yeah, what's so remarkable about Feynman's work is he can take these incredibly complex ideas
yeah,
and present them in a way that you feel like you're right there with him, uncovering these secrets of the universe.
totally. And the superposition principle, it's like, I don't know, like the gateway drug
Yeah,
to quantum weirdness.
that's a great way to put it. It really
Yeah.
challenges, everything we know about how things should behave
Yeah,
in the world.
totally.
Like, we're used to things existing in one state.
Yeah.
A coin is either heads or tails.
Right, or a light switch is on or off.
Exactly. But in the quantum world,
Yeah.
it gets a lot fuzzier than that.
So it's like, instead of our coin being definitively heads or tails, it's spinning in the air.
Right.
And it's both at the same time until we look at it.
Exactly.
That's it, right?
Yeah. You got it.
Superposition.
Feynman, in his own unique way,
Yeah.
found a way to not just describe this, but to help us visualize it
Bring it.
in a really new way. So instead of focusing on the where of a particle,
Yeah.
he shifted our attention to the how, the path it takes. That's where, things get really, really interesting.
Okay.
Feynman's idea was to imagine a particle, instead of like traveling along one path,
Yeah.
it actually explores every single path
Okay.
through space and time.
So hold on. Every path, like if I throw this pen across the room right now,
Yeah.
it's not just going like in an arc through the air.
Uh-huh.
It's also going to the moon and back at the same time.
Yeah, kind of like that. In a sense, yeah. Obviously, some paths are more likely than others.
Right.
That's where this whole probability amplitude thing comes in.
Okay, so it's not just that every path is possible, but
Yeah.
some paths have like a stronger influence on where the particle ends up.
Yeah.
Kind of like how taking the highway is probably a better bet than like
Yeah.
a dirt road.
Exactly, yeah. But here's the really wild part.
Okay.
These probability amplitudes, they're not just like
Yeah.
regular probabilities like we think of,
Okay.
They're complex numbers that reflect both the likelihood of a path
Okay.
and its wave-like nature.
So we're bringing in that whole wave-particle duality thing again.
Yeah.
My brain's going to hurt soon. I can just tell.
It's all connected, though. Think about it like this.
Okay.
Each possible path contributes a little wave of probability.
Okay.
And those waves can interfere with each other,
Right.
either like reinforcing each other or canceling each other out.
So some paths, even if they seem really out there,
Yeah.
might actually increase the probability of a particle ending up somewhere.
Yes.
Just because their waves are kind of vibing.
Exactly. Yeah. That's a good way to put it.
It's like quantum jujitsu.
Yeah. And Feynman found a way to connect these probability amplitudes to another big concept in physics, action.
Okay, before we go any further,
Yeah.
can we just remind me what action is in this context?
Well,
It's not Indiana Jones.
No, quite, no.
Okay, good.
It's more like action in physics is a way of measuring the effort of a system. So imagine like for a hiker,
Yeah.
choosing between like a steep rocky path and a longer but flatter path.
Yeah, I'm going for the flatter one.
Exactly. Less effort.
Way less effort.
That's kind of like action. The steeper path might be shorter, but it requires more action. In Feynman's formulation, the action associated with a path directly influences its probability amplitude.
Okay, so a path with like lower action
Yeah.
is going to have a higher probability amplitude.
Right.
So it's more likely the particle will take that route.
Exactly. You could almost say the
Yeah.
universe is lazy, always taking the path of least resistance.
I like that.
Right. It's
Yeah.
kind of a simplification.
Okay.
But you get the idea. What's even more remarkable is
Yeah.
Feynman connected all this to traditional quantum mechanics.
Wait, are you saying there's a connection between this whole path integral thing
Yes.
and the equations we've been using already?
There is. And it's one of the most elegant connections in physics, actually, despite their really different approaches. Feynman's path integral formulation
Yeah.
is mathematically equivalent to traditional quantum mechanics, including Schrödinger's wave equation.
Hold on. So you're saying we can describe the behavior of these particles by picturing them surfing on waves of probability,
Right.
or by adding up all the contributions from every path they could take.
Yeah.
And somehow those two things, those two ideas,
Yes.
lead to the same conclusions.
Yeah. That's the beauty of physics.
Aren't
You
you-
can have multiple paths to the same truth.
Mhm.
Feynman found this bridge between two seemingly different worlds.
Yeah.
But while his approach is really cool,
It's not perfect though, right? There's got to be like limitations.
of course, yeah.
Can't be the answer to everything.
Feynman's approach, it's brilliant, but it
Yeah.
still has challenges like incorporating certain things.
Yeah, what kind of
Like spin
Yeah.
and all the complexities of general relativity.
So it's like we have this amazing new tool,
Yeah.
but it doesn't do everything.
Right.
We're not done yet.
Yeah, we still have a lot to learn,
And
explore.
So this whole superposition thing,
Yeah.
particles existing in all these states,
Right.
what does that even mean for reality itself?
That's the million-dollar question, isn't it?
Yeah, pretty much.
It makes us rethink everything
Yeah.
and consider that maybe the universe is just uncertain,
Okay.
a place where things aren't really real
Yeah.
until they're observed.
So it's like by observing something,
Yeah.
we're forcing the universe
Right.
to pick an outcome.
Like the universe is looking at every path,
Oh.
and then we come along and we're like,
Yeah.
it's this one.
Yeah.
And it's like, okay, that's what you want.
Wow. That's a lot.
Big implications.
Yeah, it really makes you think about,
Philosophically, even.
yeah,
Yeah.
totally. And it's amazing that Feynman's work,
Yeah.
this whole path integral thing,
Uh-huh.
kind of led us to this.
Yeah, it just shows you the power
Mm.
of human curiosity,
Okay.
our need to just figure things out.
Yeah. To keep asking questions.
Exactly, even when it gets weird.
Well, on that note,
Yeah.
we're going to have to leave it there for today.
Okay.
Big thanks to everyone for joining us
It was fun.
for this deep dive
Yeah.
into the world of Feynman, the superposition principle.
It's mind-blowing stuff.
It really is. And yeah,
Until next time.
keep exploring, keep questioning, and yeah, we'll see you next time.